Hello students, today we have our first class of data structures and algorithm. In today's class we will see what is algorithm, how and why we analyze algorithm, and what are the methodologies to analyze algorithm, what are tools to analyze algorithm, and then we will see about time complexity and space complexity and overview. What is an algorithm? So algorithm is something which solves our problem. It can be anything that solves our problem. Basically in today's world, in the practical world, we have many types of problems. To solve those problems, we perform some actions, some sequence of actions, and at the end, we solve our problem. That's an algorithm. But in our subject, in the theory, in this computer science branch, what we call an algorithm is a step-by-step method to solve a problem. What are these step-by-step methods? These step-by-step methods are fundamental operations which can be performed in constant time. And any algorithm must produce a solution in the constant time, then it is an algorithm. Because if there is an algorithm which does not solve any problem, then there is no meaning of it. So a same problem can have multiple solutions or multiple algorithms. We have to choose a best possible solution. For example, we have to find a roll number in the list of all the students in the class. Let's say 25 is the roll number we have to find in the list of the all class roll numbers. We have two popular methods to find this. We check one by one every roll number in the list, or we do binary search. What we say is we use dictionary method kind of. If we have sorted list of roll number, what is the dictionary method? In the dictionary, we have all the alphabets or all the words in the lexicographic order. So when we have to search some word, what we do? We don't search that word from first page, last page, and sequence by sequence. We know that all the words in the dictionary are sorted. So we open some random page and we try to open the middle page of the book in the first. Then we see that our word is in the first half or the second half. If it exists in first half, it has some properties. Our roll number has some properties to exist in the first half or second half. On the basis of that, we decide that it must be in first half or second half, and then we discard other half and go to other half where is the high possibility of presence of our roll number. So these are two methods. We can say these are two solutions of our problem. But these solutions are implemented through the algorithm, through a step-by-step actions. What are those actions? Those actions in these two problems are comparing. In the linear search, where we comparing our objective element, which is 25, with the whole list, all the elements in the list, and maybe at the end we reach 25, or maybe 25 not present in the list, we find the solution. In the binary search also, we compare our objective element 25 with the current element at which we are in the middle, and then go to the next half, other half of that list, and then compare with another middle element, and in this way we try to find, and at the end maybe we reach some element which is equal to 25, or maybe we have traversed our whole list and 25 not present in the list. In both cases, we reach to a definite solution. Whether our roll number 25 if presents at what index it presents, or if not present, both of the solutions we can have. But in these algorithms, which algorithm is best to perform? Best to perform in what we can say, which algorithm is best to perform and we should perform, but we cannot answer it until we have information in what context. An algorithm can be better in a context 1 than other algorithm, but an other algorithm can be better than the first algorithm in some other context. For example, in the context of space and time, the binary search is a better solution. But in the context of, we can say, scalability, or we can say application, linear search is applicable at every type of input, but binary search is applicable only a sort of inputs which are, we can say, sorted order. It doesn't apply on the all types of input is list. In this case we have, so which algorithm is better? We can answer this question only when we know in what context we are talking about, we are comparing about these algorithms. Why do we analyze an algorithms? See, we have limited resources in the world. Nothing is infinite. Computer have a limited space, limited registers, or limited consumption power. We have limited time. Computers have limited time. And maybe what works for a small input may not work for a large input. What works for a small space, what that doesn't work for a large space. So correct answer is not only enough. We have to find our enough in the most optimized and efficient way. We have seen that why do we analyze an algorithm, but we know that to analyze an algorithm, we have to analyze an algorithm on the basis of some resource consumption. What can be these resources? These resources can be space, in the case of memory, RAM mostly we say, and time, and other possible resources are like power consumption, like CPU is very important resource in our domain of computer science where we solve any problem. So CPU is also a resource. So we have to take care of registers, requirement of registers, and requirement of power of CPU. So that can be a resource also. But mostly in our course of algorithm, data structures and algorithm, we analyze our algorithm on the basis of two facts or two resources. These are time and space. We have to analyze our algorithm on the basis of time and space mostly. And in that also, in these two resources, time and space also, we mostly analyze our algorithm based on the time. Why we mostly analyze our algorithm based on the time mostly? Because in the today's world, time is very crucial from the user experience perspective. Users doesn't see the space or the other resources consumption in the solution of problem or in the application. Users only experience time. They require their work, they require application to do their work in the minimal and effective time. If your program is taking a lot of time to solve their problems, it may be hard for them. So mostly we analyze time and space, and in these two resources also mostly we analyze on the basis of time complexity. What is time complexity? Time complexity is something which measures the execution time of our algorithm with respect to the input size. For example, in the linear search we have n elements and we have to search an roll number 25. So in the worst case we can say maybe our 25 not present in the list. So we, to reach a definite solution, we have to check our whole list according to the linear search algorithm, in which we compare every element with the roll number 25 and see if it equals to 25 or not. In the binary search, we will see that it takes log of n number of comparisons, and how it takes approximately log of n comparisons. But this is the time we can say. We will see that why we saying that log of n number of comparisons is approximately equals to the log of n execution time. Why we are using this type of metric, that we are saying execution time here, and here we are saying that n number of comparisons we have to do. So this is a more time, and log of n comparisons we have to do, this is a less time. Why time complexity matters? That answer I already given. For a small input, maybe our algorithm work fast. But if our input is so large, maybe it takes a lot of time. We have to take care of that also. What is the space complexity? Space complexity is about how much extra time, how much extra space or memory our algorithm is using, including arrays, variable, and other data structures. Time versus space trade-off. So an algorithm, maybe we have, in an algorithm we have two main resources, time and space, which we have to take care of. We have to choose a best algorithm on the basis of time and space trade-off. Faster algorithms may use more memory, and more memory algorithms may be slower, or maybe if we use more memory, our algorithm become faster. So we have to make a balance of time and space, so that our algorithm don't take too much of space and don't take too much of time to solve our problem, to find the solution. There are two methodologies of analysis in the algorithm. First is a posteriori analysis, other is a priori analysis. In the a posteriori analysis, we run our program on a computing system. In the a posteriori analysis, we run our program on a system. This is, we can say, very practical and very obvious way to analyze our program, or to analyze our algorithm. Here, let's say we have some algorithm, let's say we have linear search, and we have to analyze that algorithm. For that, we have a system. We have a system contains CPU, contains RAM, contains other resources like hard disk and all that. And we will run our program on that system and then analyze our time and space and other resources consumption. And for that, on the basis of that analysis, we will decide that how much good our algorithm is. In the a priori analysis, we do our algorithm most kind of theoretically. We don't need any hardware support, we don't need any physical entity, we can say, a system or computing environment. In this a priori analysis, usually we use theoretical or mathematical models to do the analysis. A posteriori, a priori, these are the two basic methodologies of analysis of our algorithm. What are the pros and cons? Simply, in the a posteriori, in the a priori. In the a posteriori, we require a computing environment. Of course, it is costly, and yes, it do most accurate analysis, but it is difficult to generalize the performance of algorithm, because the algorithm may perform fast on a better machine, but if you apply that algorithm or use that algorithm on another machine, run that algorithm on another machine which is not that efficient, maybe algorithm runs slower. So it is not a generalized way to analyze our algorithm. In the a priori analysis, we don't require any computing environment, although it doesn't produce correct, mostly accurate result, but it is approximately correct. So it is less costlier also. We can see we don't need any physical entity, or we don't need any computing environment. It is easy to generalize because we are using some very generalized mathematical models to analyze our algorithm. That's why mostly we do a priori analysis of our algorithm in our subject. Time complexity analysis. Time is very crucial resource in today's world. We have talked about that. Because space and other resource consumptions is not visible to users. Users don't take care of them. We as a developer, we if we are a firm, we are organization providing solutions to the users. We care about the resources consumption. Users don't care about the resource consumption. They only see time. We represent the time complexity using a function of input size. In this our whole course, we will represent our time complexity function using T of n, where n is the input size and T is that function representation. The function, what that function represents is, that function represents rate of change of time t with respect to the input size n, and these functions we generally call time complexity functions. And algorithm does not always take same time. its time depends on the input size mostly, or input case, what type of input we are given, or what is the size of the input. On the basis of these facts, we have three cases in our time complexity analysis. We have best case time complexity, we have worst case time complexity, we have average case time complexity. What is the best case time complexity? The best case time complexity is the minimum time our algorithm is taking. The minimum time taken by our algorithm for a input case, for a case of input. And in our case, in our course, that input called as best case input, and the time, which is a minimum time used for that case of input, the type of input, is a best case time. For example, uh, in the sorting algorithms, quicksort, I assume we already have studied that. If our input array is already sorted in ascending or descending order, it behaves as a worst case time complexity. But in the if our input is kind of randomized, it behaves a best case time complexity. So in the best case input size, our quicksort algorithm every time finds the partition in the mid of that array. We will see it in our course further, but for this point of time we have to understand this, that best case time is something we are talking is minimum time taken by the algorithm. Our algorithm will not take less than that time. It will take at least this time, this minimum time, to solve any input size n. That is the best case time, we can say. We have also worst case time, maximum time taken by the algorithm for the case of an input. We have a type of input for which our algorithm is performing our algorithm is giving solution in the maximum time. Our algorithm will not take time more than that. That time is a worst case time. Average case time complexity. In the average case time complexity, we say average of the time taken by our algorithm for all the possible input cases, input classes. Let's say we have an input array, okay, and array of integer elements. We have input, and that our input array of size n can be any case of input. Like that input in the integer array can be sorted in ascending order, can be sorted in descending order, or it can be like first half are sorted in ascending order and second half are sorted in descending order. It is another case of input. And let's say first half is descending order case of sorted and second half is ascending order sorted, or maybe all of the elements are randomized. It can be like a zigzag fashion. First element is smaller, second is greater than that, third one is smaller than the second one, and fourth one is greater than. It can be that fashion. Any case of input it can be, and those cases or those classes we are using as an input. And in those cases, in all those cases, our algorithm will perform in different way. It may take different time, but we have a maximum time taken or a minimum time taken in that whole class of input size, and an average of all the time taken for all the possible input classes. It will be the average case time, we can say. So this is all we have studied. Thank you. And after that, we have asymptotic notations and other asymptotic notations for the time complexity functions in the next class. We will study about that, and this is all about today's class. Thank you.